So this is going to be the last video, last lecture for chapter 7, and we're going to discuss the conservation of energy. Conservation of energy. It's always true. Energy can never created or destroyed. Energy will never be created or destroyed. It just transforms from one type of energy to another type of energy, then just moves throughout and do a work in the system, and then one energy decreases, the other kind of energy increases. We never gonna have you can never create new energy. So when we say save energy or new energy or something like that, is we want to have the energy in that particular form. So we're going to change that other kind of energy into that particular form of energy that we're interested in, that it's convenient to us. That's just what it means. So conservation of energy is just in general, it's true. But when you have an isolated system, or like let's say if you're in your system, there is no dissipation force applied. So let's say there's no friction force. You can ignore any friction force or any heat. The energy it's isothermal, just thermally always equilibrium, let's say. Then you have a conservation of mechanical energy. That means that you have a potential, the sum of a potential energy and a kinetic energy, the total potential energy plus kinetic energy doesn't change throughout the event, because if you don't have any dissipation of energy, like a friction does no friction force, so you don't do any work done by the friction, or no heat dissipation and things like that. Then sum of the kinetic energy and the potential energy is going to be the same throughout. So let's see, in a perfect pendulum, this is the toy from my kid. It has a magnet and you can catch the fish in a bath. But anyhow, if I raise it, right, and by raising it, I'm increasing, this potential energy has increased, okay? And then if I let go, as it goes down, it loses potential energy. But when it loses the potential energy, the kinetic energy gains. So at the bottom, when it has a minimum potential energy, we're going to have a maximum kinetic energy. So it's going to move fastest. And then as it goes up higher, it loses kinetic energy. And when it's about to turn, becomes maximum height, there's a maximum potential energy. And then when it's about to turn, what's its speed? 0. So therefore, what's its kinetic energy at that time? 0. Right, maximum potential energy, you have a minimum kinetic energy, which is 0. It makes sense, right? And then when it just turns, maximum height, speed is 0, and comes back down. So back and up, back and up. So if this is a truly conservation of mechanical energy, this the swinging motion will continue forever. So it's not a perfectly conserving all the mechanical energies, because every time we bend this string, it requires work. So the energy is being used to bend this string, right? You're doing some work. Shape deformation, right? So that's how one of the energies being lost. Of course, the friction and all that thing. So it's not a perfect system. And then if I don't swing it, if I don't put any force, then it's just gonna go, we lose all the energy, mechanical energy. But if in the ideal system, this is gonna go back and forth forever, because the sum of potential energy and the kinetic energy is the same. You have a maximum potential energy, that means you have a minimum kinetic energy. When you have a maximum kinetic energy at the bottom, you have a minimum potential energy. Maximum potential energy, minimum kinetic energy. And then about a half point, you're going to have a half of the potential energy and a half of the kinetic energy. Something like that. back and forth, back and forth, back and forth, back and forth. All right? So that's the conservation of mechanical energy. It's only at the situation that you don't have any dissipation force, then you can apply conservation of mechanical energy, which means that sum of the potential energy and kinetic energy stays the same, constant. But in general, energy cannot be ever be created or destroyed. So even you have a dissipation force or something, that means that energy has dissipated by some kind of other energy, and then it goes into using something else. Okay, so let me write that down in, I'm going to share the screen again. Okay. Okay, the last video for the chapter 7. Conservation. Okay. In general, energy, never, never, never. Energy cannot be created or destroyed. It just transforms from one form to another. Forms from one type of energy to another. So the total energy that exists in the universe stays the same. Then sometimes when there is no dissipation, of energy, like a heat dissipation, you lose the kinetic energy by dissipation through the heat, or friction force lowers the kinetic energy, decreases the kinetic energy. If you don't have that kind of forces, dissipation of energy, then you can apply something that's called conservation of mechanical energy. Right, conservation of mechanical energy. So what does this mean is that sum of potential energy and kinetic energy stays constant. Then example that I gave was that you could have a pendulum like this, right? And then when it's dropped, it's going to be this highest point. So that means that maximum potential energy. That means you have a minimum kinetic energy. If it's dropped, if starts at rest, then kinetic energy is 0. Then as this pendulum goes lower, it decreases. The potential energy decreases, and then when it's at completely at the bottom, this is at the bottom, we have a minimum potential energy, and that means we have a maximum kinetic energy. Then goes up, back up. Then at the turning point, highest point, again, you have a maximum potential energy and then minimum kinetic energy, which is 0. And this goes back and forth and back and forth and back and forth. So at here, let's say I have a potential energy. This is going to be the amount of potential energy I have. And then I could have a kinetic energy that's 0 at this location. But when it's at the bottom, the same, I use up all the potential energy and converts into kinetic energy. So the potential energy becomes 0. And then over here, again, I lose all the kinetic energy. And that becomes thing. So somewhere in the middle, I could have a potential energy and the kinetic energy, the leftover kinetic energy, somewhere in the middle. Can I have a graph? This is a question. Can I have a graph that looks something like this? The potential energy. Is this a correct graph? Can this be a correct one? Kinetic energy. But then at the bottom, I still have some potential energy. And then here, kinetic energy is 0. And then potential energy. Can this graph be possible? Can this graph also explain the energy of pendulum motion? Can this be correct? What do you say? What do you think? Right? So that's a question. All right. Let's see. This is going to be in a homework, but let's say, or maybe I'll just use my wall here. So I'm going to bang the wall. Right? I'm banging the wall right now. Banging. So I'm going to have some, immediately before my fist hits the wall, immediately before, or this too, I have some kind of a velocity, right? So that means that I have a kinetic energy right before it hits the wall. And then my fist stops. So kinetic energy, when it hit the wall, kinetic energy is, what's the kinetic energy? When it's hitting the wall. Right, it stops. So kinetic energy is 0. So immediately before I had a kinetic energy. Now it stopped. Where did the kinetic energy go? Did I lost the energy? Did the energy disappear? No. Each time when I hit it, kinetic energy is transferred to other kind of energy. One of them is maybe like when I'm hitting my palm, then I'm also using the energy that kinetic energy is doing the work to change the shape of the palm, right? So it gets pushed in. So that needs a work. The kinetic energy is changed, lost in kinetic energy equals to work done by my fist. And also, some of the energy may be used up to heat up the palm or the wall. Each time you bang the wall and touch it, the wall becomes a little bit warmer each time. So by keep pounding the wall or the desk, you can warm up because the kinetic energy is transferred into a heat energy. So energy has not destroyed. It's just changing to another kind of energy, or you do a work on the system. You could actually move the object or change the shape, so that you're doing a work. So it's doing something. So that's how energy is transferred. It's never being destroyed or created. You never suddenly, when you turn on the light, you're using electric power that's converts into thermal energy, gets warmer, and then also warmer, and also changes into a light. So that's also the energy that's transferred. All right. How about this? You have not read. This is also from the homework. How about this? Let's say I have a nail, right? And then I use the hammer to hit that nail, right? So it goes in, each bang, it goes in. What if now I'm gonna hit this nail, the same hammer, but twice of its velocity. So when I hit it with the initial V, it went into distance D. That's how much the nail went in. How much D compared to D prime? If I make it to be double the speed, if I bang the nail with the double the speed, how much deeper does the nail go in? Explain this. All right. Another example is that I'm driving a car with the speed V. And then you slam on the brake, and tire stops rotating completely. So the only force applied to stop the car is from friction. All right, so there's going to be a friction force from the ground, between the ground and a tire. That applies, and that's the reason why this car eventually stops, right? What if now you're driving the same car, but this time you're driving with the twice of the speed? So initially it took you the distance D to stop. Now, if you're speeding twice, double the speed to stop the car, again, tire stops completely, and the only force you have is from the same friction force between a tire and a road, right? So we, so now it's 0. So now if you're moving with the twice of the speed, how much of the distance you have to go to stop compared to this speed? All right, so these two are my questions to you that I hope you can answer. The discussion time. Oh my gosh, I'm sorry about that. And okay, so please answer these two questions. And I am going to show you the video of us from the physics girl, the YouTube video, and see, this is a fun video that explains the stacked up ball drop. Okay, so computer sound. I guess I want to do this. All right, here. All right, let's see.
Check out how high these different balls bounce. The basketball, the super bouncy ball, and the golf ball. Now I'm gonna try the golf ball on top of the bouncy ball, on top of the basketball. And then I'm gonna explain how it's related to a supernova. Did you see that? Probably not. So here it is again. The golf ball bounced to 28 feet. We dropped it from about 3.5 feet, so it went up 800% of its dropped height. In fact, if you consider that by itself, the golf ball bounces about 70% of its dropped height. It went as high as if it had fallen from 40 feet up. That is awesome. So how can we get the golf ball to bounce up with that much energy? Let's simplify it to these two balls. When you drop them individually, each ball starts out with some potential energy from the height of the drop. As the balls hit the ground, some energy goes into heating up the ground and some goes into heating the ball. Because that energy left the ball system, you can't get back up to the same height. But when you combine them, the tennis ball goes higher than its dropped height. Way higher. Where does it get the extra energy? As the basketball bounces, it compresses, storing elastic potential energy. As it releases, it springboards the tennis ball upward just at the right moment. This is like the double bounce on a trampoline when you jump right before someone else. You prepare the elastic of the trampoline by stretching it and storing energy, which can then bounce the jumper even higher. In the same way, the basketball stores energy in its compression and is able to push the tennis ball. But just like the double bounce preparer, the basketball can't go as high. You can see that here. It bounces even less when 3 balls are dropped together. Also, during that transfer of energy, some momentum transfers from the basketball to the tennis ball. And since the basketball starts with way more momentum because of its larger mass, the tennis ball's velocity increases by a lot, and it flies up, up, and away. Now back to the triple super ball bounce. Now you get the energy from the basketball's bounce being transferred into the bounce of the super bouncy ball, which is then transferred to the golf ball's bounce. You put the same amount of energy or momentum from 2 more massive objects into a smaller object, and it will go much faster. Epic! Just like the explosions of a supernova, which may seem unrelated, but what we just did is analogous to the process that occurs during the explosion of a supernova. Just like our more massive basketball transfers momentum to the smaller balls, energy from the dense core of the supernova is transferred in a shock wave that moves through the star to the less dense layers and accelerates them outward at a super high velocity. More massive or denser layers in the core of the supernova begin to collapse when fusion stops there. The collapse is halted when the neutrons in the core actually touch, sort of. This causes the implosion to rebound and bounce outward. You end up with a dense core left behind and these wild outer shells of star exploding outward. Pretty cool. And of course, if you try this at home, which you should, you have to make sure the balls are perfectly vertically aligned because any off-centeredness gets amplified by the 2 points of contact, which is why we sadly couldn't get the quadruple tower of balls to work. But if you put a little ring of hot glue or something similar on the balls, it helps to balance them. Happy physicsing!
All right, so I hope you enjoy the Physics Girls stackable video. You could, if you're still interested, you can Google and watch it again. Okay, so I left you with a few questions about conservation of energy, So there's a conservation energy that's general one, and then there's a conservation of mechanical energy when there's no dissipation energy. Sum of kinetic energy and potential energy stays the same. All right. And that's why when you drop a ball, drop the ball, it's never going to go up higher than where it started. Because most of the time when it drops and hits the surface, you lose the kinetic energy as heat or something, and then it won't go up as high, right? But in that case of sucking up a ball, it goes up higher than initial. And you see each time it's a mini collision. So there's a transfer momentum to bigger mass to a smaller mass. So that velocity will be higher, right? And then also there's that basketball acts like elastic force, so spring force, and then gives that elastic energy into the second ball. That's why the basketball doesn't go up as higher as it when it's just dropped by itself. So those are the things that I explain. And then I left you with a few questions about the nail, and then also with the car that's driving twice the speed. All right. So I guess I'll see you guys in the class. All right.